Okay, welcome to Chapter 2 of controlling your PS2 DCS trains with a PC. I know you're all eager to get into the hardware, but we just got to spend about 5 minutes here so you understand what it is you're going to do with this hardware. And so in order to do that, we need to first understand the DCS remote output well enough to know what it is you're trying to store. The slide you're looking at right now is the actual raw data being generated by the remote and sent to the TIU. That squiggly line is the signal, a binary signal that represents the Coors train start command. Now the TIU receives this signal and it interprets it in a RS-232 format. It's 9600 baud, one stop bit, no parity. And when it does that, it sees, in this particular case, 17 bytes of data. What I'm going to do in the next few slides is explain to you what each of those 17 bytes represents to help you better understand why it is I'm having to use the method I am and how we are going to store the data. Okay, in this slide here, what you can see is all 17 bytes. This is typical of most of the commands out of the remote. However, the number of bytes for a command when you push a button can vary between 17 to 23. This start command is a 17 byte command. Now there are bytes that never change. They're always there every time you hit the button. And those are shown in red. And that's the first 2 bytes. And they're kind of like zeros if you want to look at it that way. And it's a synchronization bytes as best I can tell. Then further on down the line you'll see another 2 bytes, and these are spacer bytes, and they are always located in the same position 5 bytes from the right side, and the last byte is the end byte for delta. That byte tells the TIU that this is the end of the message. Now when you look on this slide, you'll notice there is 2 bytes there in black called engine ID. Those 2 bytes always show up in the same position every time. Those bytes only change when you change to a new engine. Otherwise, no matter what command you send, those 2 bytes will be there for the engine you select. Okay, here you see the command bytes. The command bytes change with button selection, and these commands are the same for every engine. Those are the commands shown in blue. Now these commands can vary anywhere from 4 to 10 bytes long when they are coded in Manchesters. And these bytes, again, will only change when you select a new command. The engine bytes will remain the same. Of course, the red bytes will remain the same. Okay, this slide is the explanation of why I've had to use the method I am in generating the commands. The bytes shown in green are what are called CRC encryption bytes. They're generated by MTH remote software. And a binary computation using the CRC counter, which is the first 2 bytes you see there, and it makes some mathematical computation with the preceding 2 bytes and 6 bytes, the startup command and the engine ID, and with that mathematical calculation it generates 4 bytes of data. Now the TIU gets this message and it performs the same, it sees the counter, it performs the same mathematics because it has the algorithm, and it generates the 4 bytes and compares them to what it got. If it sees the same numbers, it says, okay, I got the right data. If it doesn't see the numbers, you'll probably get a TIU error message, or it just won't do anything. So this is why I do not use any software of MTHs or any other to generate this data stream. I'm not generating a data stream. I'm not smart enough to figure it out. What I do is I take this whole data stream as you see it, knowing that it's 17 bytes typically, but it can vary from 17 to 23, and I simply store it into a device and then recall it on demand. Okay, so what I do is I tether the remote to a device and read the output of 21 button pushes into this device. If you notice below, the arrow points to the load order that I follow, and there's a reason for this. I use the startup command first, whistle on, whistle off, coupler slack, and 1 mile per hour. And I'll explain that in a second. But you also need to note that each command, I have highlighted it in the blue boxes, the length of these commands. And you can see the startup command is 17, but you can see the whistle off and the bell off commands are 23 bytes long. Once you go over 10 miles an hour, 15, 20, 25, 30, and 40 are 19 bytes long. And mostly the remainder of them are 17 bytes long. Now, why do I use this order? Well, when you hit the startup command, it has a peculiarity. The startup command button actually sends out 23 data streams of varying lengths. However, the one you need that actually starts the engine up and makes the noise is the second data stream. So in the device, I write the little software code in my processor chip that it reads all 23 strings, but it only saves the second one and stores it. In the case of the whistle, when you push down on the whistle, it sends out a command, and when you release the button, it sends a different command. So in order to capture that, I set up the program so I hit the button and release it. Two signals go out. I capture them both and store them in this order in the memory. And then finally, the next odd one is when you roll the thumb wheel to 1 mile per hour, it actually sends out two commands. The command to go 1 mile per hour and the command to make the coupler slack clanking sound. All right, this slide shows a little bit of what I just showed you already. However, it discusses that I saved 21 commands, and those 21 commands, if you add all those up, equates to 360 bytes of data. So I have a little buffer in there. I allow 400 bytes of memory per engine. The memory stores in bytes, okay, 8-bit bytes. So I allow 400 bytes per engine. So when I store it, engine 1 starts at address 0, and I load in the 21 commands, and the last command ends at 399. I obviously know that engine 1 startup starts at address 0, it ends at address 16 because that's 17 bytes, and address 17 is the whistle on command, and so on and so forth. And I have to add the number of bytes for each one to find out where that command starts at. So I do that for engine 1. You can see that engine 2 starts at address 400 and ends at 799. Engine 3 starts at 800 and ends at 1199, and so on. And in my case, I store up to 8 engines in my EEPROM. However, I do have room for more.